Hello, my name is Sawyer West, and today we will be talking about line of sight. Line of sight is all about figuring out if two objects can see each other. For our example, let's consider two aircraft flying above the Earth. There are a lot of factors we could consider in this problem. Like, the Earth isn't smooth. There's mountains and hills and valleys that may get in the way of our two aircraft seeing each other. Furthermore, the Earth, when it spins, bulges at the equator. So we're not dealing with a sphere, we're dealing with an ellipsoid. There's also an atmosphere surrounding Earth. So when light passes through the air, it bends. So you may be able to see objects farther away than you normally would in a vacuum. Maybe these planes aren't even facing each other and would never be able to see each other. There could even be clouds that get in the way, and those change every day, all the time. If we tried to consider every real-world factor, we would never be finished this problem. We would be completely lost. So let's simplify the problem. Let's assume the Earth is spherical, and all we are given are the locations of the aircraft. Since we know where the core of the Earth is, and we know where these two aircraft are, we have these 3 points in space. And that means there is a unique mathematical plane that passes through all 3 of these points and slices the Earth perfectly in half. That means we only have to consider the mathematics on this slice to find the answer to our question. Suppose our two planes are as far apart as they can possibly be while still being able to see each other. Then their line of sight will just barely skim over the Earth. Now these two planes might have different altitudes. Plane P might have altitude A, while plane Q might have altitude B. And they're both going to fly above an Earth that has a radius of r. For now, let's consider a simpler scenario where both planes have the same exact altitude. You may notice that there are triangles here that we can work with. So we have a triangle with a side length of P to Q, which is the distance we want to find. It also has a side length of R plus A, and another side length of R plus A. Let's consider half of this triangle. So the one that has the side length of R, the side length of R plus A, and the side length of half the distance from P to Q. That's this triangle right here. Now, we don't really want that hypotenuse to be colored purple and yellow, so let's just color it all yellow for now. So if we go and make any diagrams or pictures with this triangle, it's much easier to understand what's going on. And let's call that length. We want to figure out C. Well, if we rotate the triangle, we make 4 copies of it, we can line up the hypotenuse as the edges of a square. We get this one big square, we get this little square on the inside of it, and we can relate the area of these two squares together. We have the area of the small square, which is the base times the height, so that's A plus R times A plus R. And we add the area of the 4 triangles to that inner square. And that equals the area of the bigger square, which is C plus R times C plus R, base times height. let's simplify our notation a bit. We have a plus r times a plus r, but we could just write a plus r squared. Similarly, we can write c plus r squared. Furthermore, we don't really want to go and mess around with a plus r being separated or be treated as anything other than a single quantity, because that's the length of our hypotenuse. So let's let d equal a plus r. That's going to make our diagram look like this. We also want to go and consider the area of these triangles. And we know the area of a triangle is base times height over 2. With this area of the triangle formula, we know that these 4 triangles each have area c times r over 2. So that means the area of all 4 of the triangles together is 2cr. Now we can simplify the right-hand side of our equation, which is c plus r squared, by our definition of squared. Here, we can distribute the c to c plus r and the r to c plus r. Furthermore, we can distribute out the c to c and the c to r and the r to c and the r to r. But here we have cr plus rc, and those two quantities are equal, so we can just add them together. And on both sides of the equation we have 2cr, so we can subtract that from both sides. And that gives us d squared equals c squared plus r squared. You may recognize this as the Pythagorean theorem. Let's apply this theorem to our problem. So first, since we want to find c, let's subtract r squared from both sides of the equation and take the square root. Technically, we found a value for c. However, I think this can be simplified. So let's expand out by our definition of squared, distribute that monomial over the monomial, distribute the constant over our monomial, and combine like terms. And we get this formula in simplest terms. And in the context of our equal altitude case, it's 2 times this length. But in the context of our differing altitude case, we have altitude A plugged into this equation and altitude B plugged into this equation. This means that if our planes are any farther away than this distance, then there's no way they could possibly see each other because the curvature of the Earth gets in the way. But what about the mountains? I mean, Mount Everest could get in the way. It's the tallest mountain of the world at 8,849 meters. Now, why did I bring up this exact quantity? Well, let's add that to the radius of the Earth and also subtract m from both of the altitudes. And that will look like this equation here. And this makes sense because we're taking the line of sight over a planet that is slightly larger than Earth. It's of radius r plus m. And the altitudes, they don't automatically go up with this change in elevation, they stay constant. So that's why we're subtracting off m from those altitudes. So we can simplify this equation by distributing those monomials out. And we can also combine like terms. And we can factor out a 2r from that A and M. So we get this distance here. Now we can plug in A and B into this equation and add those two together to get this other bound that we needed to find. Now that we've found these bounds, I want you to ask yourself, are these all the conditions that we need to meet for these bounds to hold true? Pause and ponder. The answer is no. Take a look at this Desmos graph. On the x-axis, we have altitude, and on the y-axis, we have the bound that is predicted, or half of the bound, I should say. So when altitude is greater than or equal to 0, we get something we would expect. As the altitude is greater, then the planes can see each other from farther away. And we get an odd edge case when the altitude is negative. In other words, when one of the planes or both of the planes are underground. It seems they can see through solid rock. What a miracle! Well, it's less a miracle and more a problem with the bounds we have on what locations we are comfortable plugging into this equation. Why does this happen? If we just consider what is happening when the x value is negative, in other words, when the altitude of the plane is below 0, then we see that we have this green line right here, which is our edge case we don't want. That is this square root of x squared plus 2xr when x is less than 0. And if we look at the terms inside, for example, the x squared term in blue, and the negative 2xr term, which is here. Now, observe this is positive in the square root, but we're going to get to why I listed it as negative here. You can see that in this intercept is directly where we start going and having problems. The reason why this is an intercept here is because this is where x squared equals negative 2xr. If this was labeled as just 2xr, this would be going in the opposite direction down here. And we would just be adding this value to this value and getting 0 right here. Well, when we square a negative number, we get a positive number, as we see right here. And we are subtracting off a negative number here, because 2 times x is negative, times r is also negative, because we're dealing with a positive radius and 2 is positive. Well, when we take a square root of a negative number, our results aren't going to be a real number. So we don't get any real solutions, and thus we don't have a problem in between 0 and this intersection right here. But as soon as this x squared term is larger than the 2xr squared, then this root term is going to be positive, and we're going to start getting solutions again. So how do we resolve this issue? In the case where our planes are in between the Earth and the maximum altitude, the mathematics we use treats this larger, maximum altitude as an Earth with a slightly larger radius, r plus m. So any solution we come up with has to reflect that this extraneous solutions that we don't want will also happen if our planes are in between the Earth and then this maximum elevation. Well, how do we solve this? Just exclude the solutions. Check to see if your altitude is below ground. If so, don't do it. That's not a solution. If your altitude is lower than the tallest mountain, you need to run the line of sight check. So what happens when we put this all together? We have our results. If the altitude of aircraft A is less than 0, or the altitude of aircraft B is below 0. In other words, if either aircraft is underground, or the distance between the planes is farther apart than the first bound we found. The planes cannot see each other, as either the curvature of the Earth gets in the way, or the planes are underground. Else, if the altitudes of plane A and plane B are both above the tallest mountain, and your planes are closer than the second bound we found, then no terrain on Earth is high enough to possibly interfere with your line of sight. Else, you need to run a line of sight check. And that is when two planes can see each other. Thank you for watching.